All right. Good. No, I need to stop saying good morning. Hello, Kagglers, and welcome to the Kaggle reading group. Is that centered? Maybe not quite. Oh no, I made me big. Sorry, let me fix that. You might be able to tell I'm a little bit tired this morning. All right, and I'm going to unplug this now that I have confirmed that the stream sounds good. It's this guy. This guy I wanted to make sure was centered. There we go. Okay, yeah, it is. Hello. It is morning for me, and I've been tired lately. I don't know, I've just got a lot on my plate. But this is one of the delicious desserts that I have on my plate, so I am very happy to be here. We are going to be starting a new paper, and we did our usual voting via YouTube and also Twitter. And in this case, which is not always the case, there was actually consensus between the two platforms on which paper we should do, and it is the AutoML benchmark. And the actual name of or title of the paper is an Open Source AutoML Benchmark. And this, like all the papers that we had in our voting choice this week, was published, and this was published at the ICML Workshop on Automated Machine Learning. And ICML is one of the big machine learning conferences. It's the International Conference on Machine Learning, although I think their Twitter tag is like ICML Conf, which is a little bit confusing. Hello from Toronto. Good morning, good morning. Hello, everybody who is here. Yeah, Bubble Ride. Hyman Sue, welcome on Kush. Hi. Little sip of coffee. We'll see how much momentum we make today. It is a big mug. I didn't shrink. I don't know why that would have been your first thought. So we've talked on the channel a couple of times about AutoML. We have an interview with Kaggle, who is an AutoML researcher in the Kaggle Coffee Chats from a while ago. I think we have some discussion of AutoML systems from the Kaggle days in San Francisco that video is up. We've got a fair amount of stuff, and it's something that I've been thinking about. And I think is becoming more and more of a topic of discussion in the field because it automates, I'm going to be honest, the part of the process that I find kind of boring, which is choosing architectures and also, and I'm sure this will be covered in the paper, so choosing your specific model architecture, sometimes also the general family of your model, and also picking parameters and your parameters are always trained. Picking hyperparameters for you. So, the difficulty with having different machine learning systems is evaluating them. And I don't know if any of you read the Medium post I wrote a while ago about a paper out of Google Research. Let me see if I can find it really quickly. And Medium meeting baselines. I want to contextualize this. Yeah, there we go. So there's a blog post I wrote a while ago about a Google AI research paper where they found that, let me zoom out a little bit so you can see this whole figure. Basically, these black points are well-established baselines, specifically in recommendation systems. These blue ones are sort of like newer, fancier models that are currently, in theory, have state-of-the-art. And then these red points down here are tuned versions of these sort of like boring baselines. And with tuning, you can see that the baseline models have beat state-of-the-art. So something that I've been thinking about a lot lately is how we evaluate models, especially outside of like a Kaggle-like context, right? Because the model that works best for your very specific problem is going to be the model that works best for your very specific problem. But more generally, how do we know what types of models are more effective and for which tasks? And that's a hard problem. And one benefit of AutoML is that, in theory, it can be a little bit Well, it's automated, so it should be a little bit more replicable. But we should be able to get around a little bit of the, I just happen to know more about how to tune this type of model, so the model that I trained is better than the model that you trained, even though they're the same underlying architecture, because that makes it really difficult to evaluate architectures. Anyway, that's a really long lead-in to sort of connect all these things together, because I know we have, at least historically, mostly been reading NLP papers in the reading group, and this is much more of a, very machine learning-y paper, and I wanted to give you guys a little bit of context. Also, a little sneak peek, there's going to be an interview with Aaron going up in the near future. I don't have my calendar handy, so I don't know what date it's going to go up, where we're going to talk a little bit about AutoML and valuation. Hello, people from all over, including Mars. I think that's a lie. My keen deductive sense has determined that is false. And this paper actually has 4 first authors. So I believe in the little doodly-oop in the bottom, I say that it's, this is Dutch, Gijsbers et al. I know I don't know the Dutch vowels good in my word saying, but it has 4 authors that had equal contribution. So Peter Gijsbers, Aaron Liddell, Janik Thomas, Sebastian Poirier, and those all had equal contributions, and then Bernd Bischel, and then Joaquin Van Schoren, I think. I actually met Joaquin at a AAAI event a while back, and he gave me some OpenML stickers that I thought were on my desk, but I guess aren't on my desk anymore. Sorry, I warned you. I'm a little out of it this morning. Sina says, do you think the future of ML will be AutoML? It's hard to say, right? So specifically for neural architecture search currently is way more expensive than just training 2 or 3 separate models and seeing which one works better. It's a lot of compute because you're training different models and comparing them to each other. So imagine that, you're doing your, and I don't know that this is 100% the way that it works for a regular neural architecture search because I'm not that deep in the literature, but you can imagine you're doing, normal stochastic gradient descent, just like you would for linear regression, whatever it is that you're training using gradient descent. And at each step, instead of, just sort of looking at your data and seeing what the fit's like, you have to retrain a new model and see if that does better on your specific task that you're trying to optimize for. And obviously that takes a lot of time, a lot of compute. As my understanding is that as the field of AutoML is advancing, being able to start in a better place and also sort of know, given the task parameters, which direction is going to be a better direction to go in is getting better and better. So it's becoming more and more efficient. And I think if it got to the point where it was very efficient, it could replace the majority of the scut work, right? The hyperparameter tuning and the experimental trying stuff out, and then you could spend more time on feature creation, and that's feature engineering, which I think is the more interesting part, personally. So I don't know. I think it's going to be an important part of the field in the future. I don't know if it's going to become the main thing that people who are doing machine learning are going to do. I don't know. I don't have a crystal ball. Let's start the paper. All right, so these are the authors, several of them from H2OAI, several of them from Eindhoven in Denmark, and then 2 of them from Ludwig Maximilians University in Munich in Germany. Abstract. In recent years, an active field of research has developed around automated machine learning, AutoML, also confusingly the name of a product. But AutoML, whenever I say it here, is going to refer to the field and the problem and not the product. Unfortunately, comparing different AutoML systems is hard and often done incorrectly. We introduce, an open, ongoing, and extensible benchmark framework which follows best practices and avoids common mistakes. The framework is open source, uses public datasets, and has a website with up-to-date results. We use the framework to conduct a thorough comparison of 4 AutoML systems across 39 datasets and analyze the results. Stas says, would be interesting to know your thoughts on different open source approaches for AutoML. I don't know. I'm not, when we read NLP papers, I'm pretty well situated in the NLP literature. Like, I have a fairly good idea of what's going on in the field. In AutoML, I'm like, I know a little bit, but I'm definitely not an AutoML researcher, so I don't have the same depth of knowledge. But we are going to talk about, I think, 4 different systems in this paper, so we'll all know more at the end. Yeah, so this is more of like, it's not quite a systems paper, but it's a paper with a software and benchmark contribution. So you can see the benchmark data sets are in here. And I know, here's the systems. There was some talk about there being a leaderboard. Did I just literally make that up? Open source, a website with up-to-date results. I don't see a leaderboard, which I'm okay with. Leaderboards don't have to be the be-all, end-all of evaluation, but something to see if we can find a little bit later on. All right, let's make it a little bit bigger. Designing and tuning machine learning systems is a labor and time-intensive task which requires expensive expertise. True. The field of automated machine learning, AutoML, is focused on automating this task. AutoML tools allow novice users to create useful machine learning models, while experts can use them to free up valuable time for other tasks. In recent years, many approaches have been developed for building and optimized model learning pipelines, or building and optimizing deep neural networks. This paper focuses on the former. Okay, so this is not going to be neural architecture search. We're not going to be talking about deep neural networks. Actually, that makes sense because I knew that it was, here's the results. That makes sense because I knew that we were going to talk about like Weka and H2O AutoML and sklearn and stuff. So, but neural architecture search is also a big part of this field. All right, the need for summarized benchmarks. Himanshu says, is this different from Google's AutoML? Yes, so Google's AutoML is a system that does AutoML. So it would be sort of, if you were going to evaluate it, it would be in this, this list of, different types of systems. It is not open source, it is proprietary. All of these systems are open source. So this is a little bit more open sourcey of a little bit more open source flavored of a paper. There is no universally best AutoML approach. Hence, we need comparisons to help practitioners select the right tools and provide objective feedback to the research community. Unfortunately, many current comparisons are lacking in several ways. The selection of datasets is often too limited in scope. Typically, we're using the same, mostly small datasets used in comparisons many years ago. So one thing that I do know about AutoML is that you need even more data than you would for a regular machine learning approach because you need to tune the model. So big data is very good. And here's Aaron. So Aaron is one of the authors. We have too many datasets to make a single leaderboard, but the results are available in various formats. Fantastic. Thank you. And Robbie says, I know about H2O. Yeah, they're cool. They have a lot of open source stuff. They have a product called Driverless AI, which is sort of similar to Google's AutoML if you're looking for tools to automate your data science process. And they also have a lot of Kaggle grandmasters, so a lot of knowledge there. Where am I starting? I wanted to say this is also having systems that are evaluated on many different data sets at the same time is sort of similar to the GLUE benchmark that we've talked about quite a bit with BERT and XLNet and GPT-2. No, not GPT-2. Was GPT-2 evaluated on BERT? I don't remember. Anyway, but that's sort of like different data sets in the same benchmark. This increases the possibility of overfitting on a specific set of data sets, creating a bias towards older data sets rather than current challenges, and may fail to show individuals' tools, strengths, or weaknesses. There was a paper a while ago out of computer vision that's like, hey everybody, we're really overfitting on ImageNet. So this is trying to avoid that problem. I don't remember that paper. Sanyam says, it has the largest ensemble of Kaggle grandmasters. That sounds right to me. Where am I? Coffee. That's where I am, and then I'm going to keep reading once I find my place on the page. Overfitting on the specific data sets. Authors may even knowingly or unknowingly select data sets on which the current systems perform well. Finally, rival methods may not have been run correctly, for instance by misunderstanding memory management and/or using insufficient compute resources. A new hope. In this work, we present an open, extensible, and ongoing AutoML benchmark to address these problems. The benchmark is completely open source and allows anyone to extend it by adding or updating AutoML systems through pull requests. Pull requests. I don't know why I did it with that emphasis. Finally, it is ongoing because we will update it with new benchmark datasets, run the experiments again when AutoML tools have and run the experiments again when AutoML tools have substantial version updates. The benchmark is accompanied by a website, which will show the latest results and other information. So that's the website I have open in the other tab right there. And what is this footnote? So the open source is just a link to the code for it. So you could go check it out if you wanted. And we haven't gotten to table 1 yet. Related literature. So here's how we're going to get where the rest of the field is right now. Abdul says data robot. Yep, another option that has some tooling available. Sorry, I'm so out of it. AutoML methods differ in their optimization method, e.g. Bayesian optimization or genetic programming. The pipelines they generate, with or without fixed structure. I don't know what that means. The library of algorithms they select from, and whether they use Metalearning to learn from runs on prior datasets, or whether they perform post-processing, e.g. ensemble correction. Pipelines they generate. So the optimization method, I think, is pretty straightforward. So Bayesian optimization or genetic programming, or whatever type of optimization you have. The pipelines they generate, e.g. with or without a fixed structure. So my guess is that picking the structure of the pipeline may or may not be part of the AutoML process. So if it doesn't have a fixed structure, then picking the structure would be part of the thing. The library of algorithms they select from, so this is sort of the things that would be available to choose from, and whether they use Metalearning to learn from runs on prior data sets, or whether they perform post-processing, e.g. ensemble and construction. Okay, so this would be learning about learning and taking a single model and then updating it and updating the way that it learns, or just or having a bunch of different. No, sorry. So that's not contrasted with this one. That's something that they may or may not do, and then they may or may not have ensembling. So there's a lot of different parameters that these different systems are varying along. Hyperparameters? They're doing different things. Table 1 shows a simplified comparison of the AutoML tools compared in this paper. The first prominent AutoML tool was AutoWeka, Thornton et al. 2013. God, I love the citation style so much more. I hate the number and bracket style that they use at NeurIPS. Drives me nuts. I've talked about it before. Because now I know, Thornton, if I see that name again, I'll be probably the same person. 2013, kind of recent in terms of most scientific disciplines, but in terms of machine learning, kind of old. Which used Bayesian optimization to select and tune the algorithms in a machine learning pipeline based on Weka. Scikit-learn, Führer et al. Did the same using Scikit-learn, Pedregosa et al., 2015 and 2011, and added Metalearning to warm start the search with the best pipelines on similar datasets, as well as ensemble construction, not correction. So they're using scikit-learning. They're using knowledge about how to learn to start in a better place so it doesn't take as long to get to a good model for your specific problem. And they also do some ensembling. Teapot, Olson et al. 2016, so we're sort of moving forward in time, optimizes scikit-learn pipelines via genetic programming, starting with simple ones and evolving them over generations. Okay, so this is where we were talking about the difference about whether or not a system uses fixed or non-fixed structure. So here you're picking the structure via genetic learning. Finally, H2O AutoML optimizes H2O components by stacking the best solutions found in a random search. So that sounds very Kaggle-y to me. So this is you're picking the best components based on your search, and then you're ensembling them together. Notable admissions from this list include AutoXGBoost, Thomas et al. 2018, which leverages Bayesian optimization to optimize gradient boosting models. XGBoost is super popular on Kaggle. I'm sure many of you have used it if you have done much Kaggle competing. Obo, Yang et al. 2018, which uses low-rank approximation to predict the best pipelines. Low-rank approximation. No idea what that is, but we're not going to talk about it. So if you want to learn more, I guess go read that paper. MLPlan, Moore et al., which optimizes Weka-based pipelines using hierarchical planning. Hierarchical planning. I also don't know what that is. This is the part of the literature that I'm like, oh, this is cool. I've never been here before. I'm like an academic tourist. And Hyperband, Lee et al. 2016, a bandit-based approach which aggressively selects configurations based on performance on subsamples of data. We do plan to include these in the next version of the benchmark. In some cases, we ran into technical issues and we are in contact with the authors to resolve them. Well, I've been there. There are also several AutoML systems which were sadly not yet open sourced at the time of the writing, yet we hope that their authors will add them to the benchmark in the near future. So they do need to have the code to be able to run it inside the benchmark. Prior efforts to create systematic AutoML benchmarks were sadly obfuscated by memory management and evaluation setup issues and lack strong baselines to interpret the results. Atin says, what does components in terms of H2O mean? Also assuming most of this is about machine learning pipelines rather than deep learning and mostly structured data, right? I think they're going to talk a little bit about the data sets. I would guess, yeah, mostly structured data. And they specifically, you might have missed at the beginning of the paper, like we're not doing neural architecture search, we're not doing deep learning, we are setting up pipelines. So these are all pipeline development systems. And the components, so H2O, the open source version, has a number of different like things. H2O open source. See if we can find the documentation real quick. Data table. Oh, I didn't know there was a data table for Python. That's cool. It's a R library that is faster for a number of reasons. H2O3. Oh, Aaron has jumped in. It means algorithms available in H2O. We use all of them and then apply stacking. This is mostly about tabular data. Sometimes it means pipelines. It depends on the tool. So yeah, and there's, LightGBM, other things, all of the sort of H2O components that you can use in the H2O library. Blah, blah, blah. Where were we? We opted instead to build an open source framework in dialogue with the AutoML framework developers to ensure the tools were properly used. So when I was talking earlier about benchmarks, and this was not for AutoML, this was for recommendation systems, but talking about how if you know a lot about the algorithm and you can tune it well, you can get like much better results. It's still a little bit small. You can get much better results than you would be able to if you were sort of just like, futzing about and working with it for the first time, which I think in some cases is, very well-intentioned and people just don't have the depth of knowledge about all the algorithms they're working with. And sometimes it's maybe less well-intentioned because you want to show that your system is the best and maybe you spend a little bit more time tuning your system and a little bit less time tuning the benchmark systems. So here, working with the developers who came up with the systems in the first place, they're probably going to get, well-tuned systems that work good. While we evaluate on fewer data sets, they are about 15 times larger on average. Okay, so not a lot of data sets compared to earlier evaluation frameworks, but big data sets, which is good because that gives AutoML systems sort of a fighting chance. Ryan says it's H2O3. Sai says, how good is production level AutoML? Well, it's pretty good. And then link to the paper, it should be, it's in the description box of the video. So if you open it up, you should be able to see a link to the website and also to the paper. Question about like how good are the production level? Fairly good. I know people are starting to use it in production, which was not the case, even like 3 years ago. So we're getting there. Where were we? Here we are. We followed best practices on how to construct and run good machine learning benchmarks, Bishel et al. 2017a, and general purpose algorithm configuration libraries, Bishel et al. 2017b, and also extend them since evaluating AutoML systems come with specific challenges. So this might be a good paper for me to just like read on my own. 2017a, OpenML benchmarking suites, and that's on archive. Oh, a lot of archive links in here. Not necessarily bad, but I personally, if there is a version available for the AutoML paper, I'm citing the version. We're looking at the version that was accepted at the workshop. Wow. What was it? More coffee. We're looking at the version that was accepted at the workshop, and if there is a peer-reviewed version and an archive version, I always prefer to cite the peer-reviewed version because it has been through more peer review. Didn't sleep great last night. All right, so that might be a good paper for me to read on my own because this is, again, just something that I've been thinking about. All right, benchmark design. Each benchmark task consists of a data set, a metric to optimize, and specific resources to use. So kind of similar to a Kaggle competition, it seems like. The resources might be training scripts, other things, I don't know. We will briefly explain our choice of each, for each. More details are available on the website, which is not this one, this one. Data sets. We selected 39 classifications, so it's all going to be classification, data sets from previous AutoML papers, Thornton et al. 2013, competitions, Isabel et al. 2016, and machine learning benchmarks, Bishel et al. 2017a. So it's the same paper that we just looked at the citation for. And they are all of these are in the OpenML benchmarking suites thing. List of benchmarking suites. So it doesn't say if it's a specific one of them. Maybe it's this one that has all of the OpenML datasets from mid-2018. No, these look like they're sort of medium to small size data sets, so they're probably not going to be big enough for good AutoML performance according to a specific set of criteria. Let me finish reading this section, then we'll go check some links out. And Aaron talking about AutoML for open source, H2O, AutoML, and H2O in general is enterprise-grade software meant for production. The sklearn-based tools can also go into production, but prediction speed is slower. And there are plenty of people who are very happy to sell you AutoML for production in various platforms. Oh no, I have dripped coffee on myself. Predefined list of criteria that we're going to go look at in just a second. Study the differences between AutoML systems. The datasets vary in the number of samples and features by orders of magnitude. Okay, so we got some wide boys, we got some, they don't have to be boys, we got some wide ones, we got some tall ones, and varying the occurrence of numeric features, categorical features, and missing values. So some of them are going to have one or the other, some of them are going to be maybe a little bit more sparse. We excluded data sets which were too easily solved with AutoML or did not represent typical AutoML scenarios, e.g. artificial data sets. So they're not including any data sets that you could get to ceiling pretty easy on, so we're probably not going to see the iris in here, the iris data set. The current list of datasets is available on OpenML, Van Schoren et al. 2014. In line with our goal to regularly update the benchmark and avoid overfitting on one static set, we set aside some datasets for inclusion in the near future. Okay, so they're trying to avoid the thing where you game the system by getting really good at like a specific subset of datasets by adding more datasets over time. We would also like to include even bigger datasets in subsequent versions, as well as regression datasets currently omitted because of computational constraints. So we're looking at like a small subsection of things. Aaron says, it's a new subset of datasets, so it's not one of the existing benchmarks from OpenML. And that was from Aaron. No worries. So I was apologizing for spelling my name wrong. I didn't even notice. I think some of you know I've mentioned a couple times I'm dyslexic, so I genuinely don't notice. Ryan says 500 data points is not too small, haha. That just seems small to me, but maybe I'm just spoiled. I would probably call that pretty small. I mean, I think I had like 300 observations for my dissertation. 300 participants? Maybe not that many. Maybe it was only 60. I could go get it. I'm not going to get sidetracked. I'm going to stay on task. But I think for a lot of machine learning stuff, that is pretty small, depending on what you're doing. Gutham says, any reason for not including regression? So it sounds like computational constraints. My understanding based on what we've read so far is that the systems are being trained and run as part of the benchmarking together using the same sort of compute pool. And so the more types of tasks that you do, the harder it's going to be to get enough compute. So it seems like sort of for technical reasons. So Aaron says, we wanted to have tiny ones. We also tried to include bigger ones, which my guess is that an AutoML system would probably do better given a bigger data set. I mean, like in data set size, then training a non-AutoML system would, right? Like as data set size increases, my intuition is that AutoML systems will improve more and will also require more compute than a non-AutoML system will given the same increase in data size. That's just sort of like, that's what feels right to me. George Horg says, what is OpenML? Is it something like proprietary ML? I believe it is like a research group? An open collaborative, frictionless, automated research learning environment. And I think it's either a nonprofit or a research group, but it's more focused on open source evaluation, having a way to evaluate and benchmark models through a centralized platform. And I don't know how it's funded. Is there a grant at the bottom? There isn't a grant at the bottom. But I know a lot of more academic researchers are involved with it. So, so people just talking about future directions for the project. We were going to look at the benchmarking data sets. So the benchmark aims to consist of data sets that represent real-world data science problems. That means we want to include data sets of all sizes, including big ones, of different problem domains and with varying levels of difficulty. So sort of a a potpourri, lots of variety. We also want to prevent AutoML tools from overfitting to our benchmark. For this reason, we plan to change the selection of benchmark problems over time. This should help prevent some of the bias that can be introduced by static benchmarks. ImageNet. I mean, also, to be fair, also Glue, which was one of the papers that was in the vote this week, was the effect of specific data sets and learning about spurious statistical correlations in those data sets in order to do real good on the benchmark. In our selection for this paper, we drew data sets. Okay, so you have some of them from the OpenML 100, OpenML CC18, and AutoML challenges. However, we did not include all the data sets. One reason was that some did not meet our criteria, more on that below. Another, that we wanted to keep some of the data sets for the future. There are also a few data sets which we wanted to include but could not include due to time constraints. Honest research methods. So the criteria are difficulty. It can't be sort of trivial to solve by any algorithm. So nothing that Vanilla XGBoost is going to work really good on. And a lot of the OpenML 100 problems are too easy, it sounds like, but also some of the OpenML CC18 problems. Real world data set, so no artificial problems, and also limiting image problems, because those problems are typically solved with solutions in the deep learning domain. However, they still make for realistic, interesting, and hard problems, so we did not want to exclude them all together. So there's some, but they're not a big part of it. And then diversity, and we didn't want to skew towards any domain in particular, so a very generalizable system. There are various software quality problems in here, and then there's a bunch of links, but adopting them all would lead to bias in the benchmark in this domain. Okay, so there's a lot of data sets which are like, how can we improve this quality of our software? And then miscellaneous reasons to exclude include label leakage. We talk about that in the Kaggle lingo video on this channel. Near duplicates, so different only in categorical encoding or imputation. So if you've already looked at a very similar data set, they're going to kick that out. Or violation of the IID assumption, so identically and independently distributed. So if there's dependency between the data sets, or dependency between the fields, and probably dependency between the data sets. Maybe. And then there are 39 classification data sets in the benchmark. Wright said, I'm Chief Overfitting Officer. I don't know how to let's just get back on track. Performance metrics. The benchmark can be run with a wide range of measures at the user's discretion. For the results in this paper, area under the receiver operator curve, AURAC, is used for binary classification problems, and log loss is used for multi-class classification problems. Mainly because these are insightful, commonly used, and supported by most AutoML tools. It is imperative that AutoML systems optimize for the same metric they are evaluated on. The measures are estimated with 10-fold cross-validation. So the big thing here is that you want to make sure that you have a system, it's trying to optimize for something, you're judging it on the thing the system was trying to optimize for and not a slightly different thing, because that's not really a fair comparison. And you also want to make sure that all the systems you're evaluating are trying to make the same number big or small. ARC, I think, needs to go up because you want more area under the curve, because that's going to be closer to the side where you have no false negatives and no false positives. And then log loss, you want to be low because loss should be low. So that's the choice of performance metrics. Hardware choice and resource specification. To improve reproducibility and extensibility, we opted to use standard M5 2x large instances available on Amazon Web Services, AWS. And this sounds like a VM, a virtual machine, 32 gigs memory, 8 CPUs, various processor speed. So not GPU enabled, it looks like. These represent commodity level hardware, which also keep the cost of running the benchmark down. Very reasonable. It is also not required to run the benchmark on AWS, however, as the benchmark can be run locally directly on a machine or from a Docker container. So they're using the same machines just for fairness, and you could run it locally or you could run it in Docker uploaded to any VM. frameworks and their configuration. Ryan says the Kaggle Days competition had a good showing of Google AutoML, and I think also there was an H2O benchmark run. I don't remember. I was so tired. I was also doing stuff at Google Next at the same time, so I was not paying as close attention as I could have. Kaggle CEO uses Google's Auto Computer Vision framework with decent success in one of the competitions. Oh yeah, Anthony is doing that right now. He's having a lot of fun, you guys. He's chatting about it. I'm just like, oh, this is so cool. I'm enjoying this. It's nice. And then Aaron says they stand a good chance in a one-day competition. With the longer competitions, humans have too much time to be creative and sneaky. Yeah, when I talked to Kwakla, I think it actually would have been just after the competition. It's in the Kaggle coffee chats. We were like, yeah, feature engineering is still like the thing that's hard and interesting, and I think will become a bigger part of data science and machine learning in the future, which I am all for. I think that's the fun part of the problem, is understanding the data set and how you can, quantify information better. All right, frameworks and their configuration. Sorry, I'm getting really sidetracked today. We require all AutoML tools to be open source. We selected the current set of tools based on popularity, ease of use, and variety of underlying techniques. We do plan to include more tools in future work and encourage all developers to add their AutoML tool to the benchmark framework. Baseline methods include a constant predictor, which always predicts the class prior, so just whatever's most likely, an untuned random forest, and a tuned random forest, for which up to 11 unique values of max features are evaluated with cross-validation as time permits, and evaluated by refitting the final model with optimal max feature values. So you just got baseline random forest. Sounds like no boosting. And then the tuning is 11 values of max features. So they're only one of the, only one parameter is being tuned. There's up to 11 depending on time. And then the optimal value of those 11 choices is the one that's picked. And Aaron does remember. I used vanilla H2O AutoML for 100 minutes on the San Francisco Kaggle Days competition and came in 8th, if I remember correctly. Cool. So yeah, there were other systems as well. And the Ryan points out that the data set was tabular data, where I'm really going into the memory banks here. I believe the labels were unknown. So the columns were labeled, but you didn't know like what they represented in the real world. And it was a manufacturing data set, something from I think. So it was some sort of value that it was measured from the real world, but you didn't have access to that information, so you couldn't know a lot about manufacturing and do real good. I vaguely remember this. It's coming back to me. So these are they have some reasonable benchmarks, and then all of the methods are being evaluated using the same compute, the same data sets. The AutoML tools were all used with their default hyperparameter values and search spaces, since most users will use them this way. True. The expectation are hyperparameters which specified the exception are hyperparameters which specified available resources, which were fixed to a specific number of cores, memory, and total runtime. So just out of the box, and the only thing that was being changed was the amount of compute available to make sure that it was fair across all of the different systems. Very reasonable. This was done to allow a more practical comparison, and because it is practically impossible to homogenize the search spaces for each tool. That makes sense, because they are doing very different things. So it would be hard to say that a genetic algorithm and Bayesian optimization, how would you make those equivalent? Because they're fundamentally different in the way that they work. So besides amount of time that you allow them to run, it seems deeply weird to try and equate the search spaces of those two, because they're not. I don't know. It's weird. Bubble Ride said, "I prefer grad student descent over AutoML. To be honest, I mean." it might be cheaper. Grad students are not that expensive. As someone who was a grad student for a pretty long time, Ryan says the variables were all anonymous. Oh, this was for the AutoML competition at Kaggle days. I was in first up until they released an additional set with a bunch of anonymous features. So more data was added in the middle of the competition as a additional wrinkle. I think that happened while I was giving a talk at another conference at the same time. So. It is important to realize that no two tools share the exact same search space or optimization method, so from this benchmark, no conclusion can be drawn about those. Open source extensible framework structure. In developing the benchmark framework, we made sure that it is easily extensible with new frameworks or datasets, so it should be easy to add stuff add stuff later on. New AutoML tools can be easily wrapped and included. Each of the current tools required less than 100 lines of wrapper code. It's pretty good. Adding a dataset that is hosted on AutoML only takes 3 lines of code. New additions are not evaluated automatically. So you can add things, but it's not all going to be run right away, which makes sense. Even only with 4 systems. And I don't know that they have said how long the runtime was, but that's still, it'll take a minute. Metalearning. AutoML frameworks may use metalearning to learn about good configurations across datasets. An AutoML framework which uses datasets of the benchmark in its metalearning process will have an unfair advantage on them. We did not decide how to resolve this issue and leave it as future work. From our selection of frameworks, only AutoSKLearn uses metalearning, and we indicate affected datasets in the results. So if you are training your system on how to learn using a bunch of different datasets, if it has seen one of those datasets when it's learning how to learn, it'll probably do better at it later on. And they just, that's for the future, and it's only going to affect AutoSKLearn, excuse me. All right. Results. Oh, are we already on results? Man, we are breezing through this. This is much easier to read than the last couple of papers we read. Results. We ran 2 benchmarks using a time budget of 1 and 4 hours per fold, respectively, for a total of around 8,000 hours of computation time, which sounds like a lot, but if you think about, the new Amazon trained, oh God, I don't even remember, Bert? I think Amazon was like, we trained Bert in an hour, but we used 5,000 cores, or something like that for one system. So that's not completely unreasonable. The 4-hour raw results are visualized in Figure 1. These results are very similar to the 1-hour ones, bringing only slight score improvements for some frameworks, especially Teapot. AutoWeka is showing signs of overfitting when running longer, especially on multi-class problems. There is no AutoML system which consistently outperforms all others. On some datasets, the performance differences can be significant, but on others, the AutoML methods are only marginally better than a random forest. The variance of the per-fold scores can be quite large. On the Dionys? No, that looks like Greek. And Helena datasets, all frameworks perform worse than a random forest. Oh. Both have more than 100 quite unbalanced classes, which seem to be a weak spot for current AutoML techniques, at least under log loss. Oh, interesting. Because the scores vary across tasks, we also normalize them such that the constant predictor is 0 and the tune random forest is 1. The constant predictor is 0. Shown in Table 2, these scores reflect the relative improvement over the strongest baseline, with a score greater than 1 better than the strongest baseline. Okay, so 0 is you always predict the majority class. 1 is the performance of the tuned random forest. If you get less than 0, you're doing worse than chance. So maybe fix your stuff. If you get between 0 and 1, you're not doing better than a reasonable baseline. If you're doing better than 1, you're beating the baseline. Generally, these scores are very similar across methods, all being relatively close to the tuned random forest baseline. Also, the distance between 0 and 1 is going to differ based on the specific is going to differ based on the specific data set. So in data sets where tuned random forest is a huge improvement, you're going to need to do a much, much bigger improvement to get a value of 2. But on data sets where tuned random forest was only a little improvement, if you can do, that much better than tuned random forest, then you'll get a good score. Is why I think they're doing that. None of the AutoML systems outperforms an untuned random forest across all problems, though in most cases they are better than a tuned random forest. Unless otherwise specified, random forests were built with 2,000 estimators and scikit-learn 0.20 defaults. Okay. AutoWeka has the poorest performance out of the tested AutoML packages under the tested conditions. I believe it was also the oldest. Note that these results were obtained using a rather generous time budget. We hope to add anytime performance evaluation curves in the future, but this is not supported by many of the AutoML tools. So taking a sample at different time points in the training, I think is what they're talking about, and then plotting that on a curve so you can see how the effective training time affects the performance of the tool. Finally, we can observe that on some datasets, some AutoML tools perform significantly better or worse than others. At the moment, we can't draw clear conclusions about which data properties explain this behavior beyond what we'd observed above. We aim to study this further by including more datasets. Basically the point of this is that AutoML is not a solved problem, right? None of these open source projects are doing significantly better than a reasonable baseline on everything. There are some things where they are doing better, and it sounds like there's some things where they're doing worse. None of them outperformed an untuned random forest in all problems, although in most cases they are better than a tuned random forest. So generally they are an improvement, but it's not like unilaterally just use the AutoML, it's going to do better than, a reasonable baseline. So heading back to the chat, is the compute the same? I believe that the resources and the time were the same across benchmarks. And it was, Ryan, NVIDIA, it was not Amazon, sorry about that, trained Megabert and GP2 in under an hour. They trained a GP2 8 billion that had multiple times more parameters than the original GP2 large, so a big one. And the ridiculous amount of compute, just like a lot of compute. And then Aaron's chiming in, yes, they fixed the amount of time per tool. And Java required for AutoWeka, yes, it's a Java-based tool. Was there ever comparison between, and this is Atin, was there ever a comparison between where the AutoML tools were allowed to run to completion, and if those results were compared well, and if any difference was observed? I'm guessing, what would completion be? It's like, I'm imagining it's most machine learning things where it's sort of going to like at some point kind of come to a stable area. But if you just keep letting it go, it's going to overfit, right? Yeah, Atin said, most tools do not have a concept of completion, thus we use a time limit. Yeah, you could keep having it run forever, then you'd have a perfect model of your data set that you spent, 10,000 hours of compute to train. All right, let's look at these results. Sai says, is Elon aware of AutoML? That should make his life easier to getting the AGI. I don't think he knows about machine learning. I'm sure he's fine. I don't think he has deep domain knowledge about machine learning. Okay. So these are color-based. So my apologies if you are not getting the differences. Blue is AutoSKLearn, orange is AutoWeka, green is constant predictor, so predicting the prior. Red is H2O AutoML, the open source one. Purple is random forest. Brown is teapot. Wow, that looks very similar to me. The purple and the brown is a little bit better. And then pink pink is the tuned random forest. So, and you can see that there's some data sets where there's a lot of variation, even between folds on the same model. So this blood transfusion data set. And some where everybody's at the ceiling, like the APS failure data set, where everyone's just pretty much doing real good. And these are binary classification problems, so these are the ones where you want your score to be up because it's, oh, rock. Yes. Yes, high is good. So here we are at ceiling. Yeah, and there are some where, oh, here, so these ones here, AutoWeka is doing significantly, yeah, that does look significant, doing significantly worse than the other models. The newer AI one, it looks like people are not doing amazingly at. No, none of the systems are doing particularly good at, and they're also sort of tightly clustered, so that might just be a hard problem. Yeah. Ryan says, not sure if I missed this, but I'm assuming they're doing a trust chain split, and then the final scoring is on some sort of holdout. Otherwise, them not improving on an untuned random forest is a bit surprising. Yes, I believe that each of these little light dots is a fold, and they're doing cross-validation, and then the dark dots are probably the mean or the median of the runs. Oh, let's read the figure caption first. Scores obtained on each data set by each framework on each of 10 folds. So yeah, they are doing cross-validation. On the left are binary, on the right are multi-class classification problems. Opaque diamonds represent the average score across all fields. So yeah. And then for multi-class, it was log loss, which I think lowers, but... accuracy... 0 and 1. A perfect model would have a log loss of 0. So yes, lower is better. I don't know, I just had a moment where I was like, do I remember math? Do I have a good domain knowledge in machine learning? Sorry, it's going to get weird for a sec. Nope, there we go. So if we're looking over here, lower is better. Looks like the shuttle data set, folks are pretty much close to ceiling. Also, notice that this is log, because it's log loss. Interesting, yeah. So it does, just eyeballing this, it looks like AutoWeka, which again is the oldest system, is actually underperforming the constant prediction a lot of the times. Although at least in this one, it looks like there was one... Because here's the average, and here's like the spread of the other trials. So it looks like this was probably one or two just really bad runs dragging it down. Oh, not this one though. It did not do a great job on this one. Interesting. So I would say if you're looking for an open source AutoML tool, maybe go with something a little bit more recent than Weka. There are a couple where it did, the best or close to the best, but overall, maybe not your first choice. But yeah, just a lot of variation. Different systems are doing well on different problems. Sometimes they're beating a reasonable baseline. Sometimes they're not. So lots of work to do. All right. Oh, and here's just the same thing as numbers you can look at that on your own. Conclusion. We presented a novel benchmark for AutoML frameworks, which is open source, extensible, both in terms of AutoML frameworks and tasks, and ongoing, publishing all the latest results online. Current results already highlight several avenues for further AutoML research. On some datasets, none of the frameworks outperforms a random forest within 4 hours, and high-dimensional or highly multi-class problems are often challenging. So this is probably a good, if you happen to have a dataset you can open source in this general category, add it to the benchmark. In future work, we will include more frameworks and tasks, especially larger data sets and regression tasks. And Peter would like to acknowledge funding by the Data-Driven Discovery of Models program run by DARPA and the Air Force Research Laboratory. So this is American Department of Defense program that was providing funding. So, oh wow, we got through that in an hour, even with all my weird asides. So this is a I mean, the main contribution of this paper is the system itself, which you can check out here. And there are more results as well, so you can check it out as a CSV, and there's also some visualizations. So we could look at a couple of those. Woo-woo. Looks like the title is a little bit cut off here. Why isn't this iframe scaling with the rest of it? GitHub, why isn't this iframe scaling with the rest of it? So I can't look at all of this at the same time. But this is looking at the performance of different systems on binary classification problems and sort of the relationships of systems to each other. So remembering that the tuned random forest is 1 and that anything below 0 is going to be worse than the predicting the prior. So yeah, and again, it looks like there's patterns both in terms of data sets where systems tend to do pretty well. Most systems tend to do pretty well, or most systems tend to do, not quite as good. But there doesn't seem to be as much of a pattern in the differences between the systems, except that AutoWeka is not quite as, not doing quite as well all the time. Which, and again, was one of the, I think was the oldest system. Yeah, so AutoWeka was from 2013, and then the other systems were from 2015, 2016, and 2017. So they had, time to build on more of the research, and I think it's actually really heartening that the older system is doing a little bit less good than some of the more recent systems, because that suggests to me that there is progress in the field, and that even in this very diverse set of tasks, the newer systems are tending to do a little bit better. So that's cool. Yeah, so, hi, it's Joaquin? No, I know I'm saying it wrong. Joe, hi, good to see you again. And then people are chiming in and letting me know that, yes, loss 0 is better. I don't know, I just had a moment of pure panic where I was like, I've forgotten all metrics. We're talking about cross-validation. Just says, Weka tends to require a much longer runtime than more recent AutoML tools. The results had a 4-hour time limit. Okay, so if there was longer running time, we might see better results. Although I will also say that it did good faster for me is something that's going to make me more likely to use a tool if I don't have to sit around as long waiting for it to train. So. But maybe if there had been a longer training time, we would have seen better results from the AutoWeka. Adam says, was there any conclusion made around which algorithm component won most of the time? If it was XGBoost, then does it pretty much make sense to always use that component and just tune the hyperparameters? So AutoXGBoost was not included. I believe the ones which would have the different components would be H2O AutoML. I think selecting components is also part of AutoSKLearn. I don't know if they have a... I know that there is a gradient boosting option in sklearn, and I also know it was added pretty recently, in the last... around the time that Kaggle Days in San Francisco was held. So I don't know whether it's going to be included in AutoSKLearn or not. But no, there's no discussion of that in this paper, at least. Oh, and Aaron actually answered. Great question. We would like to study it further. And Aaron says, from experience in H2O AutoML, we have seen XGBoost winning most of the time from the set of base models. The stacked ensemble, including all the models, usually does the best, though, which is also, I think, what tends to happen in Kaggle competitions. Joaquin says, whenever you have a time limit, you can get better performance by designing your search space better. That's reasonable. If you know that you've lost an earring, it's easier to find it in a 1 by 1 foot space, as long as you know that you lost it in that space than it is in a 20 by 20 foot space. if we are, let's say, on grass, I think that's a reasonable thing to try and search for an earring in, where the earring is the local minima. And I guess also you have a metal detector, so you can kind of tell if you're getting close or not. And also your earrings are metal. I don't know. I went a little bit off the rails there. And Aaron says, the AutoSKlearn authors have also reported that XGBoost is the best algorithm selected by their tool. I don't have the reference, but it's in the paper written by them. So the AutoSKlearn. So that must have been pretty recent then. Maybe this year? Robbie says, AutoML can't do feature engineering? Well, I mean, I think in the broad research area of AutoML, feature engineering is one of the problems. I also, again, I'm not a researcher in this field, but my gut instinct, my feeling is that it's going to be the hardest part of the problem. So I don't think we've had as much luck there. And Aaron says, some tools include it, some don't. All right, I think I've caught up with the chat. I don't know why I decided it was the cache in my head. If you are interested in using this tool, feel free to give it a try, kick the tires. The benchmarking site is, it's linked in the video description, and also if you just search AutoML Benchmark, it should come up, and you can dig a little bit more into the results and the data sets, and maybe, add some data sets. If you've got an open source AutoML system, just see how it does. Give it a try. All right. So I'm going to wrap it up here for the... Oh, Jupyter says 2017. I think that's when XGBoost... I'm going to look this up because it's going to bother me if I don't. XGBoost sklearn added. All right. Integration with scikit-learn 1 year ago. So it would have been like 2018? Scikit-learn, K-fold, randomized search, just tree and split. The easiest thing would be for me to go and, XGBoost regressor. Nope, that's still XGBoost. So this is the XGBoost package, not the integration in scikit-learn. I'll go look at the release notes at some point and figure it out. I'm sorry, I'm all over the place today. Thank you for joining, everybody. I hope this was helpful. I certainly enjoyed reading it. I'm going to go and read that this top one here. Balaji? No, Bishel. The Bishel 2017A. So this one on the OpenML benchmarking suites where they talk about best practices in benchmarking, because that's something that, again, I've just been thinking a lot about. So this is added in my personal reading list. And next week, we'll start a new paper, and I might make an executive decision and just make it EfficientNet, because people have been asking for EfficientNet for so long, and CNNs are not an architecture I've played around with much, so it's going to be a slog for me, but it'll be good, and I'll learn a lot. So that might just be the next paper that we do is EfficientNet. So, all right. Thank you very much, and thanks for hopping in, Aaron and Joaquin. I know I'm saying it wrong. I'm so sorry. I'm really happy that you could be here to help answer questions. And I will talk to you all on Friday if you tune in for my live coding, or next Wednesday for the next paper reading group, where we will probably do EfficientNet unless something big comes up between here and then. All right. I'll talk to you guys then. See you on Kaggle. Bye.